Light shapes our world in ways both familiar and profound. It colors the sky, carries information, and reveals the hidden structures of the universe. Yet, light is more than what meets the eye. Its dual nature, sometimes behaving as a wave, at other times as a stream of particles, has challenged and inspired scientists for centuries. Among the most remarkable achievements of modern physics is the harnessing of light through lasers, tools that create beams of extraordinary purity, coherence, and intensity. From delicate surgery to precise manufacturing, from streaming data across oceans to scanning barcodes at the checkout, lasers have become woven into the fabric of daily life and scientific discovery. To understand how such a focused force became possible, we must begin with the nature of light itself, a journey that traces the curiosity of thinkers and the bold leaps that led to one of the defining inventions of the 20th century. Light has long inspired wonder, admired for its beauty and shrouded in mystery. For centuries, great thinkers pondered what light truly was, how it traveled, and how it might be harnessed. The story of lasers, their origins, inventors, and extraordinary impact, begins with the quest to understand the very essence of light itself. In the 17th century, this debate became a lively rivalry between two of science's leading minds. Isaac Newton, whose work revolutionized physics, believed that light was made up of tiny, discrete particles. He imagined these particles traveling in straight lines and bouncing off surfaces, much like miniature billiard balls. Newton's experiments with prisms were pivotal. By passing white sunlight through a glass prism, he showed that it could be split into a rainbow of colors. This display not only revealed the hidden composition of sunlight, but also gave us the term spectrum, which today describes the entire range of electromagnetic radiation. Yet Newton's view was not universally accepted. Christian Huygens, a contemporary of Newton, argued instead that light behaved as a wave. According to Huygens, the ripples of light spread out in all directions, much like waves in a pond after a stone is tossed in. The debate between the particle and wave models simmered for over a century, with each side gathering evidence to support its claims. The tide began to turn in the early 19th century, thanks to experiments by Thomas Young and François Arago. Their work showed that when light passed through narrow slits, it created patterns of bright and dark bands. This phenomenon, known as interference, could only be explained if light were indeed a wave, capable of overlapping and combining in intricate ways. For many, the wave theory seemed to have won, but science is rarely settled for long. As the 20th century dawned, cracks appeared in the wave-only view of light. In 1900, Max Planck introduced a radical idea: energy, including that carried by light, was not continuous but came in tiny packets, or quanta. This quantum theory was further advanced by Albert Einstein in 1905, who explained the photoelectric effect, where light knocks electrons out of metal, by proposing that light itself must be made up of discrete particles, which we now call photons. With these advances, a richer picture of light emerged. No longer just a wave, nor just a particle, light was understood to possess a dual nature. Depending on how it was observed, light could act as a wave, spreading and interfering, or as a particle, delivering energy in indivisible bursts. This wave-particle duality became a cornerstone of quantum mechanics, revealing that the universe at its most fundamental level is often stranger than everyday experience suggests. As these discoveries unfolded, scientists began to map the full range of electromagnetic radiation. What we see with our eyes' visible light is just a narrow slice of a much broader electromagnetic spectrum. This spectrum stretches from the long, gentle undulations of radio waves, through microwaves and infrared, across the rainbow of visible light, and on to the energetic ultraviolet X-rays, and finally the shortest, most powerful gamma rays. Each region of this spectrum has its own properties and uses, but all are united by the fact that they are forms of electromagnetic radiation traveling through space at the same remarkable speed. Though the groundwork for understanding light's nature had been laid, a crucial question remained: could human ingenuity control and harness light in ways never before imagined? The answer would come from a deeper exploration of the quantum principles first uncovered by Planck and Einstein. In 1917, Einstein introduced the concept of stimulated emission. He described how, under certain conditions, an excited atom could be prompted to release its energy in the form of a photon, and that this photon would be identical in color, direction, and phase to the one that triggered it. This principle, though theoretical at the time, was the seed from which the laser would eventually grow. Decades passed before technology caught up with theory. In the 1950s, Charles Townes and his colleagues built the first device to harness stimulated emission, not with visible light, but with microwaves. This device was called the maser, short for microwave amplification by stimulated emission of radiation. It amplified microwaves to unprecedented intensities, opening new avenues for research and communication. Inspired by the success of the maser, Townes, Arthur Shallow, and others began to imagine a similar device that could work at optical frequencies, what would become known as the laser. The path from idea to reality was not straightforward. Many believed that building such a device was impossible. Yet, in 1960, Theodore Maiman succeeded where others had failed. Using a synthetic ruby rod, a flash lamp, and a carefully arranged set of mirrors, he constructed the first working laser. When powered, the ruby emitted a brief but brilliant pulse of red light, coherent, intense, and startlingly pure. At first, Maiman's invention was met with skepticism. Some questioned its practicality, even dismissing it as a solution looking for a problem. But this skepticism did not last. The term laser, an acronym for light amplification by stimulated emission of radiation, was quickly adopted thanks to Townes and his colleagues. The laser's unique properties, its coherence, intensity, and ability to focus energy into a narrow beam proved to be not just scientifically fascinating but also immensely useful. Within a short time, lasers found applications in science, medicine, and technology. They became tools for precise measurement, delicate surgery, and even the reading of digital information. The invention of the laser is widely regarded as one of the greatest achievements of the 20th century, a triumph of both scientific understanding and technological innovation. From the earliest debates over the nature of light to the brilliant pulse of Maiman's ruby laser, the journey reflects the power of curiosity, persistence, and the human drive to illuminate the unknown. As we look back on the birth of the laser, we see not just a new tool, but a profound leap in our ability to shape and use the fundamental forces of nature. Imagine, for a moment, a room filled with atoms, restless, energetic, each harboring its own secret store of energy. Left to themselves, these atoms resemble a crowd at a concert before the show begins. Some are lively, some are calm, and the overall mood is chaotic. Now, picture what happens when a single spark of light enters this room. In the world of lasers, that spark sets off a remarkable chain reaction, transforming ordinary light into something extraordinary. At the heart of every laser lies a process called stimulated emission. It is a concept as elegant as it is powerful. When an atom is excited, meaning it holds more energy than usual, it waits, poised to release this energy. If a photon, a tiny particle of light, happens by and matches the energy difference exactly, it does not simply pass by unnoticed. Instead, it nudges the excited atom, stimulating it to emit a second photon that is a perfect twin of the first. Both photons now travel together in perfect step, matching in energy, direction, and even the rhythm of their oscillations. This is the essence of light amplification, the process that gives the laser its name and unique character. But this remarkable choreography only unfolds when the conditions are just right. One crucial requirement is what scientists call population inversion. In most situations, atoms prefer to stay in their lowest energy state, their ground state. The trick to making a laser work is to tip the balance, to create a situation where more atoms are in an excited state than at rest. Achieving population inversion is like convincing most of the concert crowd to leap to their feet, ready to join the music rather than sit back passively. This is no easy feat. It requires pumping energy into the atoms, coaxing them into higher states of excitement. How this energy is delivered depends on the type of laser. Some lasers are energized optically, using bursts of light, while others use electrical currents or even chemical reactions to pump energy into the system. When energy is pumped into the gain medium, the special material at the core of the laser, it raises a large number of atoms into excited states. In a classic three-level laser system, such as the one used in the earliest ruby lasers, the process unfolds in 3 steps. First, optical pumping excites atoms to a very high energy level. These atoms almost immediately relax down to a slightly lower but still excited, metastable state. This state is stable enough to allow a significant accumulation of excited atoms, making it possible to reach population inversion. From there, the atoms are primed and ready for stimulated emission, with each photon that passes through triggering the release of more identical photons. The gain medium is the heart of the laser, the stage where all this action takes place. Its properties determine the color, or wavelength, of the laser light, as well as many other characteristics. Gain media come in many forms. Some are solids like crystals or glasses, others are liquids or gases. Each type of medium brings its own strengths and quirks. For example, certain gases might be chosen for their ability to emit light at a specific wavelength, while solid-state materials can offer durability and intense beams. Surrounding the gain medium is the optical cavity, sometimes called the resonator. This structure typically consists of 2 mirrors facing each other, with the gain medium sandwiched between them. One mirror is fully reflective, bouncing all light back into the cavity, while the other is only partially reflective, allowing some light to escape. As photons race back and forth between the mirrors, they pass repeatedly through the gain medium. Each time they traverse the medium, they stimulate more atoms to emit identical photons, causing the light to grow in intensity. Only the light that builds up at just the right wavelength and phase survives this journey. The rest is filtered out or lost. Eventually, a portion of the amplified light escapes through the partially reflective mirror, emerging as the laser beam we recognize. Inside this optical cavity, a remarkable transformation occurs. Ordinary light, a chaotic jumble of colors and directions, is filtered and sculpted into something far more disciplined. The photons in a laser beam march in lockstep, their waves perfectly aligned, a property known as coherence. The light is also monochromatic, consisting of a single, pure wavelength. And because the photons all travel in the same direction, the beam is highly directional and can remain narrow over long distances. These qualities, coherence, monochromaticity, and directionality, set laser light apart from any other source. The process that makes this possible is called optical amplification. As the photons pass through the gain medium, stimulated emission causes their numbers to multiply. Each photon acts as a catalyst, prompting more atoms to release their energy in the form of identical photons. The result is a dramatic increase in the intensity of light, a single spark transformed into a brilliant, focused beam. The details of how population inversion and optical amplification are achieved can vary from one laser to another. In some cases, electrical pumping is used. An electric current passes through the gain medium, exciting the atoms or molecules directly. In other designs, powerful flashes of light provide the necessary energy. There are even lasers that use chemical reactions to create the needed conditions. Regardless of the method, the goal is always the same: to achieve and maintain population inversion so that stimulated emission can dominate over all other processes. Every laser, no matter how complex, is built upon this trio of essential components: the gain medium, which defines the laser's identity, the pump source, which supplies the energy to fuel the action, and the optical cavity, which organizes and amplifies the light. Each part plays a vital role, and together they create a device that seems almost magical in its ability to transform chaotic energy into a precise, powerful beam. When you see a laser in action, whether it is a pointer dotting a wall or a beam slicing through metal, it is easy to forget the subtle dance of atoms and photons unfolding within. But at its core, every laser is a triumph of physics and engineering, harnessing the principles of stimulated emission, population inversion, and optical amplification to turn ordinary light into something truly extraordinary. Lasers, remarkable in their diversity, exist in a dazzling array of forms, each defined by the material at its core, the gain medium. This single choice, whether crystal, gas, liquid dye, semiconductor, or specially prepared fiber, determines how a laser behaves, what color of light it emits, how much power it can deliver, and where its unique strengths are best applied. To appreciate the ingenuity behind modern lasers, let us explore their main types, examining how each is constructed, how it operates, and what makes it suited to its particular role. Imagine first a block of crystal or glass, its interior infused with special ions. This is the realm of solid-state lasers, a class that includes some of the most powerful and widely used lasers in science and industry. The classic example is the neodymium-doped yttrium aluminum garnet, or NdYAG laser, where a rod of YAG crystal is doped with neodymium ions. When energy is pumped into this solid, often by intense bursts of light, the neodymium ions become excited and, through stimulated emission, release their energy as a focused beam of laser light. These lasers can produce both steady, continuous beams and extremely brief, intense pulses depending on their mode of operation. Their high output power and durability have made them essential tools for medical procedures, precise measurements, and heavy-duty manufacturing. Notably, the very first laser belonged to this family, a ruby laser, using a synthetic ruby crystal as its gain medium, made history with its brief, brilliant pulse. Gas lasers, by contrast, have a certain transparency, both literally and figuratively. Their active ingredient is a gas, excited by an electrical discharge. Picture a glass tube filled with carbon dioxide, and you have the foundation of a carbon dioxide laser, one of the workhorses of industrial cutting and welding. The gas mixture inside the tube, energized by electricity, emits powerful beams of infrared light. So powerful, in fact, that entire factories rely on them to slice through metal and other tough materials. Other gas lasers, such as helium neon or helium neon lasers, are far more modest in power, but valued for their steady, reliable output. The red glow of a helium neon laser, for instance, is often used to align machinery or make precise optical measurements, its stability and clarity making it a quiet favorite in laboratories and workshops. Argon lasers, another member of this group, are known for their vivid blue and green beams, used in scientific research and medical treatments. Taking a different approach, semiconductor lasers, or laser diodes, compress the entire operation into a tiny chip of engineered material. Here, the gain medium is a junction between two types of semiconductor. Imagine a sandwich where electrons and holes meet in the middle, releasing photons as they recombine. Gallium arsenide and related compounds are often used to create these junctions, which are energized simply by running an electric current through the device. The result is a compact, efficient, and versatile source of laser light, small enough to fit in the palm of your hand or even on the tip of your finger. This makes them the backbone of modern communications, where laser diodes transmit vast quantities of information through optical fibers. They are also the unseen engines inside barcode scanners, DVD players, and countless other everyday technologies. Their efficiency and size have brought laser light out of the laboratory and into daily life. For those seeking a broader palette, dye lasers offer something truly special: tunability. Instead of a solid or a gas, these lasers use an organic dye dissolved in liquid. Imagine a flask of glowing solution, shimmering with potential. When this dye is excited by a flash of light or another laser, it emits photons across a wide range of wavelengths, not just a single color. By carefully choosing the dye and adjusting the setup, researchers can tune the laser to almost any color within a broad spectrum. This property is invaluable in scientific research, especially in spectroscopy, where sweeping across different wavelengths allows for the investigation of atomic and molecular structures in exquisite detail. Dye lasers can also produce ultra-short pulses of light, opening the door to studying incredibly fast processes in chemistry and physics. Among the newest and fastest-growing members of the laser family are fiber lasers, which represent a sophisticated evolution of the solid-state approach. Here, the gain medium is not a bulky crystal, but a flexible strand of optical fiber similar to the fibers that carry internet signals around the world doped with rare earth ions. Light travels along the length of this fiber, interacting with the dopants to produce laser emission. Fiber lasers are renowned for their efficiency and precision. They generate beams that are not only powerful, but also exceptionally well controlled in shape and quality. This makes them increasingly popular in industrial settings, where their ability to cut, weld, and engrave with minimal maintenance and high reliability is greatly valued. With all these types, it becomes clear that each laser is a product of deliberate engineering, tailored to its intended use. Some are built for brute strength, carving through steel; others for finesse, measuring the tiniest shifts in position or probing the mysteries of living cells. The choice of gain, medium solid, gas, liquid, semiconductor, or fiber, sets the stage for everything that follows, from the color and intensity of the beam to the efficiency and cost of operation. Pumping methods also matter. Whether the energy comes from light, electricity, or another source, it must be matched to the medium for optimal performance. No single type of laser reigns supreme. Instead, each offers a unique blend of advantages and limitations. Solid-state lasers boast high power and versatility, but may require careful cooling or alignment. Gas lasers can achieve impressive powers or produce beautifully stable beams, yet their size and need for pressurized gases can be drawbacks. Semiconductor lasers are marvels of miniaturization and efficiency, but their output power is generally lower than some other types. Dye lasers are tunable and capable of generating ultra-short pulses, though they require careful handling of liquid dyes and regular maintenance. Fiber lasers combine efficiency with precision and are rapidly expanding their role in industry. What unites all these variations is the principle of harnessing the quantum dance of atoms, ions, or molecules to produce light that is not just bright, but extraordinarily precise and controlled. The landscape of lasers is as diverse as the challenges they are called upon to solve, and understanding these types lays the foundation for appreciating how lasers have found their way into everything from high-tech manufacturing to the frontiers of fundamental science. Imagine a world without lasers. It would be less precise, less connected, and, in many ways, less extraordinary. The laser's journey from scientific curiosity to indispensable tool is quietly woven into modern life, shaping everything from how we communicate to how we heal, build, and even entertain ourselves. At the heart of a laser's impact lies a unique blend of properties: remarkable precision, unwavering directionality, and light of a single, pure color. These attributes grant lasers a versatility that few inventions can match, opening doors across nearly every field of human endeavor. In medicine, lasers have transformed the art of healing. Surgeons wield beams of light as scalpels, making incisions so fine that the surrounding tissue is barely disturbed. Minimally invasive surgeries are now commonplace thanks to this precision. A beam can vaporize a tumor, cauterize blood vessels as it cuts, or reshape the delicate surface of an eye. Procedures like laser-assisted in situ keratomolysis rely on the pinpoint accuracy of lasers to correct vision, allowing millions to shed their glasses and contact lenses. In dermatology, lasers target unwanted hair, tattoos, or blemishes, while in dentistry, they remove decay with far less discomfort than traditional drills. Advanced diagnostics also owe much to lasers, illuminating tissues at just the right wavelength to reveal subtle changes or guide intricate interventions inside the body. Step into a modern factory, and lasers are everywhere, often unseen but essential. Their ability to cut, weld, and engrave with micrometer precision has revolutionized manufacturing. A laser-guided machine can slice through steel, trace delicate patterns onto electronic components, or weld seams in automotive parts with consistency. The same properties that make lasers suitable for surgery: purity, focus, and power enable manufacturers to craft complex designs that would be impossible by hand or with mechanical tools. Additive manufacturing, also known as three-dimensional printing, has embraced lasers as well. Here, tightly focused beams fuse layers of metal powder, building intricate shapes from the ground up, part by part. This process not only saves material, but also allows for the creation of objects with internal structures and geometries that defy traditional manufacturing techniques. Yet the laser's reach extends far beyond the operating theater or assembly line. It underpins the very infrastructure of modern communication. Every second, vast rivers of data, voice calls, emails, streaming videos flow invisibly through networks of glass fibers that crisscross continents and oceans. At the core of these fiber optic cables, lasers pulse on and off with breathtaking speed, encoding information as flashes of light. Their purity and directionality mean that signals can travel great distances with minimal loss or interference, making possible the high-speed internet and global connectivity that many now take for granted. Without lasers, the digital age as we know it would simply not exist. This technology also finds its way into daily routines in countless, often overlooked ways. Walk into a supermarket, and the rhythmic beep at the checkout counter is the voice of a laser scanner, swiftly reading barcodes to keep lines moving. Slip a disc into a digital versatile disc or Blu-ray player, and a low-powered laser reads the microscopic bumps and pits that encode music, movies, or data. Even the humble laser printer, a fixture in homes and offices, uses a finely focused beam to draw images and text onto a drum, transferring toner with accuracy. Optical mice glide smoothly, their movements tracked not by a rolling ball, but by a tiny laser illuminating the surface beneath. Entertainment, too, has found a place for lasers, whether in dazzling light shows that paint the night sky or in the creation of holograms that seem to float in midair. Scientific research, meanwhile, has been invigorated by the precision and adaptability of lasers. In spectroscopy, lasers probe the fundamental structure of atoms and molecules, revealing secrets about the universe at the smallest scales. Metrology, the science of measurement, relies on laser beams to gauge distances with exactness, underpinning technologies from construction to satellite navigation. Lasers serve as the heart of atomic clocks, the most accurate timekeepers ever built, and play roles in experiments testing the limits of physical laws. Beyond these familiar and foundational uses, lasers are also at the cutting edge of specialized innovation. Light detection and ranging, or LiDAR, harnesses rapid laser pulses to map landscapes, guide autonomous vehicles, and enable precision agriculture. In atomic physics, laser cooling allows researchers to slow atoms to near absolute zero, opening new frontiers in quantum science. The very tools used to build and maintain medical devices often rely on laser-based manufacturing, ensuring that the instruments of healing are themselves crafted with precision. It is the laser's essential qualities: its monochromaticity, its coherence, its ability to focus energy into a tight, intense beam that make all of this possible. These properties are not mere technicalities. They are the reason a laser can perform surgery without damaging surrounding tissue, transmit data across oceans without garbling the message, and etch serial numbers onto tiny components with microscopic detail. The same beam that reads a barcode in a grocery store can shape titanium in a jet engine, carry a phone call around the world, or illuminate the inner workings of a living cell. The power and flexibility of lasers have woven them into the fabric of 21st century life, often so thoroughly that their presence is invisible, yet their impact is unmistakable. From the operating room to the factory floor, from the internet's backbone to the checkout counter, lasers have become indispensable. Their story is not just one of scientific triumph, but of daily, practical transformation proof that the most profound technologies are those that turn the extraordinary into the everyday. And as research pushes forward, the versatility and significance of lasers continue to expand, shaping the world in ways both spectacular and quietly essential. The story of lasers has always been one of possibility, of taking a spark of theoretical insight and turning it into an engine for discovery. As we look ahead, this sense of possibility only grows. The future of laser technology is not simply a continuation of what has come before. It is a leap into realms that, just a few decades ago, would have sounded like science fiction. Even now, the landscape is shifting beneath our feet, with breakthroughs that promise to redefine what lasers can achieve, how they are made, and the very questions scientists can ask of the universe. One of the most striking frontiers is the development of ultra-fast lasers capable of producing pulses that last just femtoseconds, or even attoseconds. For perspective, a femtosecond is to a second as a second is to about 30 million years. These flashes of light are so brief that they can capture and influence phenomena at the level of electrons orbiting atomic nuclei. The implications are profound. Ultra-fast lasers have become a kind of strobe light for the quantum world, allowing researchers to observe chemical reactions as they unfold, probe the structure of materials at the atomic scale, and create new states of matter that exist only fleetingly. In precision manufacturing, these lasers offer a degree of control approaching the limits set by physics itself, enabling the fabrication of structures and devices with features measured in mere nanometers. In imaging, ultra-fast pulses reveal details invisible to longer-duration light, opening new windows into biological systems and the fundamental workings of nature. Yet even as lasers push the boundaries of speed, a parallel revolution is unfolding in the world of the very small and the very strange quantum technologies. Here, lasers are not just tools but essential enablers. They create, control, and stabilize quantum states, the fragile superpositions and entanglements that make quantum communication and computation possible. Quantum communication systems, for example, rely on lasers to generate photons that can carry information in ways fundamentally secure against eavesdropping. In quantum computing, lasers manipulate the quantum bits, or qubits, that promise to solve problems beyond the reach of classical machines. Quantum sensing, another rapidly advancing field, uses lasers to detect minute changes in the environment, measuring time, gravity, or magnetic fields with extraordinary precision. The challenge here is not simply to make lasers brighter or faster, but to fine-tune their properties with exquisite care, ensuring that each photon is exactly where and what it needs to be. The future of quantum technology is intertwined with the future of lasers, a partnership just beginning to reveal its potential. As lasers become more versatile and powerful, they are finding roles in some of the most ambitious technological projects of our time. One such vision is laser-driven nuclear fusion. The idea is as bold as it sounds, using intense laser pulses to compress and heat a tiny pellet of fuel until atomic nuclei fuse, releasing vast amounts of energy. If realized at scale, laser fusion could provide a source of power cleaner and more abundant than anything currently available. The technical challenges are immense, but each advance in high-powered laser systems brings this goal a little closer. Another area where lasers are poised to make a transformative impact is advanced chip manufacturing. As the demands of microelectronics become ever more exacting, lasers are being used to etch and pattern materials at resolutions approaching the atomic level. This is not just about making smaller or faster computers. It is about inventing entirely new kinds of devices, from sensors to circuits that harness the unique properties of quantum mechanics. In high-energy density physics, lasers generate conditions akin to those found in stars or the cores of giant planets, enabling scientists to study matter under extreme pressures and temperatures without leaving the laboratory. Alongside these headline-grabbing advances, a quieter revolution is underway. High-power fiber lasers are becoming more common, valued for their efficiency and stability. The expansion of laser-based 3D printing continues as industries discover the benefits of building objects layer by layer with geometries that were once impossible. Healthcare, too, stands to benefit as lasers become more precise and adaptable, promising new diagnostic and therapeutic techniques. Increasingly, artificial intelligence is being integrated into laser systems, guiding, optimizing, and controlling their operation in real time. This merger of laser technology with machine learning is likely to yield systems that are smarter, more flexible, and more reliable than anything seen before. All of these trends point to robust growth in the global laser technology market. Demand is surging not only in established areas like manufacturing and telecommunications, but also in healthcare and the emerging realm of quantum technologies. As lasers become more deeply embedded in critical infrastructure and daily life, the importance of policy and safety considerations is coming to the forefront. Many laser technologies are dual-use, serving both civilian and military purposes, which raises complex questions about regulation, standardization, and ethical deployment. The need for new standards, especially for industrial and consumer applications, will grow as lasers become ever more powerful and ubiquitous. On the research front, the quest continues to design novel laser sources with tailored attributes. Scientists are working to craft beams with specific spatial patterns, spectral properties, and pulse shapes, adapting the output to the needs of particular experiments or applications. On-chip lasers and metasurface lasers, which integrate photonic devices directly into microchips or exploit engineered surfaces to shape light, are in development. New materials are constantly being explored, with the aim of boosting performance, lowering costs, or enabling seamless integration with existing technologies. The future of laser technology is not a single path, but a sprawling network of possibilities. It is a story of tools that illuminate new corners of knowledge, shape matter at unprecedented scales, and link the quantum world to the technologies of everyday life. Each breakthrough brings fresh questions and opportunities. Will lasers unlock practical fusion energy? Will quantum lasers underpin a new era of secure communication or powerful computation? How will the integration of artificial intelligence and photonics change the tools we use to see, heal, and build? These are not idle speculations, but the very real frontiers being explored in laboratories and industries around the world. What remains certain is that the evolution of lasers will continue to inspire curiosity and innovation for decades to come. As researchers and engineers push boundaries, they invite us all to imagine and then realize a future where the control of light is limited only by our creativity and determination. The laser, born from a marriage of theory and ingenuity, is set to remain a beacon for discovery, guiding us into the unknown with each new pulse of possibility.